Hi. So, another ice snow lecture or whatever that is. Um, all right. So this is what I started talking about last time in class. We're looking at continuously differentiable functions. So again, suppose that we have some open set. Then we have a function f defined on U. So open set in Rn, it's valued in Rm, so between any two Euclidean spaces. We say it's continuously differentiable, or C1, sometimes C1 of U, or depending on how much you want to include in the notation. If it's differentiable and the derivative is continuous, right? So it's differentiable, meaning differentiable at every point. So at every point, there is a linear operator that best approximates the function. And so I have a function. The f prime is really a function from U onto the set of linear operators, right? And we're asking for this function f prime to be continuous, right? So how this operator moves is continuous. And again, as we saw before, right? It's the continuity of of functions either to or from the set of linear operators. Now, normally the metric there is the operator norm, but you can also just consider this a big Euclidean space, right? An n times m dimensional Euclidean space, and this function. So you can think of each one of these operators as a matrix, right? And so this function is a function from U onto the set of matrices, n by m, or actually m by n matrices, and that is continuous if and only if the coefficients are continuous functions, and the coefficients of the derivative, as we've seen, are the partial derivatives, all the different partial derivatives of all the different components of f, right? So things that look like this, right? All right. So how do we, how do we tell something is continuously differentiable? There's actually an easy way of doing this in terms of just the partial derivatives, right? So it's not always true that if partial derivatives exist, that the function is differentiable, right? All the partial derivatives could exist, but the function might not be differentiable. The function might not be even continuous, right? But if the partial derivatives exist, and if they're continuous, then the function is differentiable, and of course, then the derivative is continuous, right? So that's this proposition over here, right? It's stated as an if and only if, right? So it's saying that f is continuously differentiable if and only if the partial derivatives exist everywhere, all the different partial derivatives, and are continuous, right? First order partial derivatives, not, we're not doing higher order stuff now, right? So just these guys, all of these guys exist and are continuous. Now, sort of, one part we already have, right? So that's really the start of the proof over here, right? If the partial derivative, the other direction, if the function is continuously differentiable, right? Well, then we know, we've already proved that that means that so it's differentiable in particular, right? So we know that all the derivatives, all the partial derivatives exist, right? So differentiable implies existence of partial derivatives, right? That part works. So that means that we have that all of these things exist. Now, if this is also continuous, then as I just said, right, that means that the coefficients of this matrix are continuous functions. And so the coefficients of that matrix are precisely the partial derivatives, right? So we have the direction, this implies this, right? Oops. this, right? That's what we have so far. Now, for the other direction, suppose that that we have partial derivatives and they're continuous. Now, it's enough to really prove that that implies that f is differentiable. Once we have that f is differentiable, once this function exists, then we already have, right, that then once it's differentiable, these are the coefficients of that matrix and they're continuous, so therefore this mapping is going to be continuous, right? So really the key thing is to show, and that's what we're saying, you know, over here, right, that you know, if we show, I should just go up to here. If we show that f prime exists at all x, we are done, right? So so we just need to, you know, look at a particular x and show that at that point we have that the derivative exists, right? Using only the fact that these guys exist and are continuous, right? So that's what we need to do. To do this, we do an induction on dimension. So first, when n is 1, so when we're starting this over here, if it's a function of a single variable, right? That means that the derivative, over here is just this column vector, right? And the way it acts, right, is just by multiplication of that column vector by a number, right? Now, it's fairly easy to see that, you know, that's if the derivatives exist and are if the partial derivatives exist, that's the same thing as having the derivatives existing, right? I mean, essentially, you know, you could first think of even when m is 1, right? And it's just the one variable version of it, right? And then, you know, the partial derivative is actually the derivative, right? So it's not hard to prove if n is equal to 1. And so, we leave it as an exercise, but it's a fairly easy exercise. So suppose that the conclusion is true in one less dimension, right? So we've proved it in R n minus 1, right? So if we start with an n minus 1 dimensional set, right, and we have a function on that, the conclusion is true. Now, so what we're going to do is we're going to basically restrict to the first n minus 1 variables and apply what we know, right? So what we could do is basically, look at, we fix the last coordinate, right? And then we have a function of n minus 1 variables, right? Now, to do this, this is going to be useful just in terms of the notation, to think of R n minus 1 as a subset of Rn, right? So when we're looking at these operators, right, we're going to think of Rn minus 1 as a subset of Rn by basically identifying the vector in Rn minus 1, right? So this is n minus 1 numbers, right? This is vector. And we're just going to identify it with the set where xn is 0, right? It's not true that, normally this really is, this point. I mean, those are two different things, but for the purposes of this proof, we're going to identify them. And you could think about how to do it without this. We just need to come up with some notation for this. But we're basically, if we think of a vector in Rn minus 1, we think of it as lying in Rn, right? And it's useful in this case to do it. Now, if we take the matrix of partial derivatives, right? We want to show that that's actually the derivative, right? Right now, it's just a matrix of partial derivatives, right? Need to show that it is actually the derivative, right? What we could do is we could split it up. We could split it up into the matrix of the first n-1 columns, and then we're going to split off the last column, right? Call it V. So we're going to have A prime is the first n-1 columns, and V is the last column of this matrix. All right. So as you know, we're trying to show that some limit is 0, right? So let epsilon be given, right? Now, we have the induction hypothesis. We're saying that the theorem works in n-1 variables. That means that there is some delta such that for every k in Rn-1, right, if k is within delta of 0, then I have this thing, right? That's that's basically looking at the derivative in Rn-1. I'm fixing, I'm basically just going in the, just moving in the first n-1 directions. I'm not allowed to be moving in the last direction, right? And so, right, this thing is supposed to go to 0 as k goes to 0, right? So that's what I'm giving. That's just writing that statement, right? And and for that, right, if the derivative exists, right, I mean, it is in the first n-1 variables, right? It is precisely this A prime, right? So that's why I have A prime here, right? Okay. So now the partial derivatives are continuous, right? That's what we're assuming, right? This wouldn't be true otherwise. We need to assume something. So we're assuming the continuity of the partial derivatives, right? So now suppose that delta is also small enough. I mean, we can, if this is true for all these k, it's, we could make delta still smaller as long as it's positive, and we would still have this, right? We just have it for fewer k, right? Who cares? So we can make delta small enough such that basically, this thing by continuity of this guy at x, right? If I move within delta, right now h is in Rn, so it's moving in any direction, including the nth direction, right? So as long as I don't move further away than delta, that I have that the nth derivative is no more than epsilon, and I'm doing it for all j, right? And there's only finitely many components, right? So I can just pick the smallest delta that makes that work, and that also makes this work, right? That's that's what I'm saying here. All right, now if we have a vector in Rn, what we could do is write it, and this is where I'm using this identification again, right? K is a vector in Rn-1, so really a vector in Rn-1, 0, right? So n-1, components and 0, right? Plus T is just, whatever is going to be the last component, right? So I'm basically writing this H as the first n-1 numbers. That's the thing that I'm calling K, and then T, right? That's the last component is T, right? So here En is the standard basis vector, right? So, right, so this is the, this is where these guys are living, right? And I'm gonna, assume that H is in norm less than delta. All right, then what we have, you can check that that means that k is also less than delta, right? I mean, it's if you compute, this is just the Euclidean norm, right? The Euclidean norm of this thing is really the Euclidean norm squared of k plus t squared square root of that, right? So the Euclidean norm of k is definitely less than or equal to the norm of h, right? And the only way that that would be equal is if t was 0, right? But anyway, so we have that k is also less than delta, right? So we have this estimate, right, to begin with. That's why we're doing that, right? And now, also, if a times h, that's really what I want to show, that this approximates the function, right? Well, I write it in terms of a prime because I know something about a prime, and v, right? So I write it as a prime k plus tv, right? So that's just a different way of writing down ah, right? So I look at the numerator of the expression that I want to go to 0, right? And all right, so I write down. So I take this expression and I write it down in terms of the k and the t and the en and all that, right? So, and I, add and subtract something, right? So I have this ah is this plus this, right? So this ah I'm going to subtract. I'm going to subtract the a prime k here, and I'm going to subtract the tv here. And what I have, so this, let's see, this guy, that's this thing, right? And this guy is out here, right? So what I add and subtract is this f of x plus k, right? Now, the reason why I'm doing that is that over here, I'm looking at the value at x plus k plus going in the nth direction a little bit. And then, so I'm really starting at x plus k. And over here, I'm starting at x going in the first n minus 1 directions. This is really where we need this continuity. All right. So, okay. So I use triangle inequality here, right? I have these two guys, and now, right, this thing will give me that the numerator is less than epsilon times norm of k, right? So I get rid of this bit over here, and I have this guy left, right? So far, so good. Okay, now what I'm gonna do is I'm gonna use the mean value term, right? So as I'm moving from basically as t moves, right? Well, as not maybe t, but some other variable moves between 0 and t, right? T is less than or bigger than 0. I don't know exactly, right? But it's either 0 t or t0. So as I'm moving between that, right, in that interval, I apply the mean value term, right? So there exists some, and I'm just gonna call it theta j, right? And so for each j, I get a different theta j, such that this guy, right? This difference, the guy that I have in the previous, on the previous page, right? In that estimate, right? I can write it as equals to t times the length of this interval, right? Assigned, right? So it's the b minus a from the mean value term times the derivative, right? That I'm getting when I'm moving in the nth direction, and that's the partial derivative with respect to xn, right? And now it's evaluated at this theta j, right? So that's just the mean value term, right? So now, I'm assuming that norm h is less than delta. So therefore, this thing. I mean, I had this estimate with t, and theta j is basically less than the absolute value of t, right? I mean, it's smaller. So this guy is definitely less than or equal to h, right? I'm making one of the components of this vector smaller, right? So that means that is still within delta, right? So now we can finish this estimate. We have this guy less than or equal to this, right? That's what we got on the previous slide or previous page. It's not a slide really. All right. So now what we do is, well, let's write down what we have, right? So here the first, this guy, we use this equality, right? That gives us this, right? And then minus TV, that gives us this, right? V, remember, is the last column of this matrix that's our supposed derivative, right? So it's matrix of partial derivatives, right? It's exactly, that's what it is, right? And so now we have, let's take stock of where we are. Well, we look at this, right? The t, I can just move the t out. I'm gonna get an absolute value of t here, right? Because I'm gonna get m of these. That's where I'm getting the square root of m, right? So I'm really looking at this minus this without the t, right? And here, this is where I'm using the continuity of f at x, of the partial derivative of f at x, right? Namely the nth partial derivatives, right? So we have that the difference of this minus this, because the difference between x plus k plus theta j en and x, right? I mean, that's just the size of this vector, right? That's less than delta, right? That's what we did over here. That means that difference is less than epsilon, right? That's the continuity of this guy, right? So that's where this epsilon is coming up, right? Now we're basically done. I need to write it in terms of age, not k. But really, what I can do is I can just norm age definitely bounds norm k, right? So I can replace this with age, right? Also, absolute value of t is bounded by norm h, right? For the same reason, right? So I can bound both of these guys from above by norm h, right? Now if I do that, I get this expression over here, and I claim I'm done, right? Why am I done? Well, if this is the numerator of the expression that I want to go to 0, this is the denominator, right? This maybe without the epsilon, this guy, right? The norm h. So if I divide this whole thing by norm h, I get that this over norm h is less than or equal to some constant. M is fixed, right? Some constant times epsilon, right? So for every epsilon, there is a delta such that I have that this less than this is some quantity that is basically less than something times epsilon. So I could have picked it so that it would be so that I would get epsilon over here, right? If I some of these estimates, instead of getting epsilon in there, I had I guess epsilon over square root of m plus 1, but it doesn't really matter, right? I can make it arbitrarily small, right? So this divided by this becomes arbitrarily small, and therefore a is the derivative of f at x, right? Which is all that I needed, right? That's as I said, once we have that the function is differentiable at x, well, it's differentiable at every x was arbitrary, and then I know that the derivative is actually the matrix of of partial derivatives, and we actually have just proved that too, right? And then we know that that matrix has continuous components, and therefore f prime is continuous, right? Because the components of that mapping, as a mapping into the set of matrices, is continuous. All right. So how is this? This is the way that you commonly show that something is differentiable is that you look at you compute the partial derivatives. It's not enough, but if you can show that the partial derivatives are all actually continuous, then you know that the function is differentiable, right? And most of the time, at most points, most functions that you encounter in any sort of applications are gonna be just that, right? So that's then you just have to worry about the discontinuities of these of the partials. That's where you have to be careful. But if you have a function defined in terms of some expression in the variables, you just sort of compute with just calculus, right? You figure out what the partial derivatives are, and you stare at them. You figure out where are these functions continuous. And generally it's wherever you're not dividing by zero. That's what happens in most of these expressions, right? And that gives you all the points where this function is going to be differentiable, actually continuously differentiable. And then you might have some other points to maybe check, right? All right. So one application of this is, for example, polynomial, right, in several variables, right? So polynomial in variables x1 through xn. So it's just some expression like this, right? It's if I'm saying it's of degree d, that means that this these monomials, right, should not be of degree bigger than d, total degree, right? So it's some expression like this. This is a finite sum, right? And so we're claiming that this is continuously differentiable, and well, how do you do that? Well, so you start. And there's a bunch of ways of doing that, right? But you could do this, like in each variable separately. So, for example, in the nth variable in xn, right? So you could rewrite this expression out here as an expression like this, right? Where, you're basically writing it as a polynomial in x and j, right? You're grouping all the terms that have the same power of xn, right? And so you can always write the polynomial in this way, right? These guys are polynomials in one less variable, right? And namely, they don't involve xn, right? So if you differentiate with respect to xn, you get an expression like this, because the derivative doesn't fall on this pj. Well, that's again just a polynomial. That's just a funky way of writing a polynomial. And so all the partial derivatives, you can do this with any one of the variables, right? So all the partial derivatives are again just polynomials, right? And we know that polynomials are continuous because all the algebraic operations are continuous. Therefore, all the partial derivatives are continuous. Therefore, polynomials are not just differentiable; they're continuously differentiable. All right. So that's it for today.